I'd like to welcome you to the third installment of the annual speaker series hosted by the Royal Ontario Museum of Paleontology and its Cooperating Society. Today we're hosting Donald Brinkman. Sorry, we're not hosting Donald Brinkman. We're hosting the other Donald, Don Henderson, who will be talking on dinosaurs in the movies. Don is originally from Scotland, immigrated as a wee lad in the early 70s with his family to the Lower Mainland, British Columbia. And Don still gets back there occasionally to visit family and indulge in his favorite sport of extreme tobogganing. Donald has had a circuitous route getting into paleo, like many of us. His Bachelor of Science degree was actually in geology and physics, University of Toronto. He worked for a year doing sonar work, decided that really wasn't what he wanted to do for the rest of his life. He then went to the University of Calgary and spent a couple years taking biology and paleontology courses. That allowed him to then go to the University of Bristol, where he pursued a PhD looking at biomechanics of theropod locomotion. After that, several postdoctoral stints, Johns Hopkins University, back at the University of Calgary. And then at the end of September, or end of January 2006, was hired as the Tyrrell's curator of dinosaurs. And he's been with us ever since. Don describes himself as a generalist when it comes to his research. A couple major themes of his work is that as a footloose and fancy-free bachelor with no commitments other than to his tortoise and his vegetable garden, he often gets dispatched to the field to investigate site reports. So he's done a lot of work with public reports, dinosaur fossils, footprints, and doing work in some of our industrial mines, the Corite mine and some of the oil sands mines up in the Fort McMurray area. And has been involved in some of the descriptions of specimens from there, including our fabulous 3D nodosaur out in the gallery. His other main interest is looking at the biomechanics of vertebrates, extinct vertebrates, and how these organisms functioned and lived. He does a lot of work doing computer modeling using software programs that he writes and tweaks himself, and has done a lot of work looking at things like buoyancy, swimming abilities, flying abilities, and so forth. And I think we're probably going to hear some of that when he critiques what he loves about dinosaurs as they're portrayed in the movies. So Don, if you're ready for your close-up, lights, camera, action.
Mercy buckets. So some of you might have seen the title of the talk is Dinosaurs in the Movies, but there's a bit more to it. What I really sent Francois was a title like that. So I've liked monsters ever since I was little. Since I've been 6 years old, Doctor Who's been my favorite TV show, only because of the monsters. And it wasn't until I was about 9 or 10 I realized, oh, if you actually pay attention, there's a story as well. But so I broke this down into 5 categories. Dinosaurs in the movies tend to be too hungry, too bland, too big, they show bad anatomy, and they're moving much too fast. So I'm going to look at each of these 5 topics. So let's start with a really basic one, color. So dinosaurs have been popular in the movies since motion pictures first started in the early 20th century, but they're always portrayed, even right up to the recent King Kong and the newer Jurassic Park ones, they're always these monochrome, bland things, without fail. But when you look at modern reptiles today, they're really colorful. And we know they don't just use color in their skin. If you look at their retina, you can see the types of cells in their retina, the cone cells that detect different wavelengths of light. They can sense color and they know to use it. And this diagram is a cladogram. It shows our modern thinking about how animals are related to each other. And this is so modern living reptiles, and dinosaurs slot into this perfectly well. So we can start to make inferences. If we see certain features in all the living examples, what can we say about the extinct forms? And with dinosaurs, we've also got living forms today. We call them birds. There's about 10,000 different kinds. And today, we know that birds are super colorful. They really make use of color. Crows are black, but there's something else going on. Birds see a wider range of wavelengths of light than we do. So, it's not right to show dinosaurs as bland gray for several reasons. And so you're going to notice that I'm really going to give it to Jurassic Park films. They've been made in the last 25 plus years. The science of paleo and zoology has really come along since these animals were first found. I'm absolutely astounded at how crummy a lot of the dinosaurs are. The shapes are fine, except for maybe the posture and the limbs, but color, they really fall down. Here's a modern lizard today, the basilisk, one of the types of basilisk. It's got display structures down its back and on its head, and it's colorful, it's got blotches, it's got stripes. These animals can see color and they know to make use of it. And just a word of caution, I'll say later, you shouldn't really use lizards as a model for dinosaurs. Dinosaurs are not just bigger lizards. But anyway, in some features you can use them, and I think color and display is one of them. So that's a stegosaur, bad stegosaur. Here's another one. Let's go back 30 plus years, Triceratops. Bland, boring, brown. Here's a modern horned, well, I shouldn't say horned lizard, it's a chameleon, but it's got 3 horns on its face. And it's making use of color. The horns are obviously, in both the dinosaur and the lizard, they're for display, for show. There is some possible evidence that Triceratops may have been locking their heads together and pushing, but there's more for, don't even think of it harassing me. There's 2 things I just want to mention about the chameleon there. When I was about 12 years old, I had this great idea that Triceratops hadn't gone extinct. It had evolved into the Jackson's chameleon. But at the time, I thought there was a problem that I always thought evolution went from small to big. I couldn't see how could you shrink down a Triceratops that's as big as an elephant down to a lizard as big as your hand. And the other thing, when I first learned about these lizards, I only read about them. And I was always pronouncing it as a chameleon. And then I was watching this David Attenborough show, and he kept talking about chameleons. And then I twigged. But I still think of them as chameleons. Okay, here we are, come forward 30 plus years from 1966, and we've still got boring, drab, brown Triceratops. Everything else about it is amazing. Look at the detail. It's great, but it needs some color. Again, look at the rest of the body of Jackson's chameleon. These things are using color. Another boring example. You would think with all these spines and plates and armor and decorations around the head, why wouldn't this animal use color to help signal? It's either signaling to other ankylosaurs or to male-male signaling or male-female signaling. If they've got the potential to have color, why wouldn't they use it? And you don't just need reds and yellows to make yourself distinctive. You can look at a modern example like the starred tortoise. It's got distinctive markings, quite visually. When it's out in the open, it's very obvious. But I think a lot of that might be camouflage in the dry, grassy habitats. That would break up the animal's outline. But anyway, there's more going on than you would think from the Jurassic Park models. So some of you might think, but what about giant tortoises? They're bland and monochrome. But I think there's something different going on with them, that they don't have any spikes or frills or plates. They're not trying to exaggerate their appearance. And also, they live on these relatively small islands. There's no major predators. I think their ecology is very different. They probably don't need color. They certainly can see color, because colors of foods is really important for tortoises. They really like reds and yellows. And just come back to the Stegosaurus example. If you're going to put plates and spines on your body, wouldn't you want to exaggerate them and make them more obvious with color? So we've got living dinosaur down the bottom right. It enhances the effect with color, with the yellow on the crest there. And the lizard, the anole up there, it doesn't always display that flap, that red flap. It's called the dewlap. It's only erected when the animal wants to use it. But if it comes up red, it really jumps out. And I think you can imagine these plates in Stegosaurus, they must have had some color. So you have to ask, why do we have bland, dull, movie dinosaurs? And I think this is the reason. The big animals we have today are all these monochrome large mammals. And except for us primates, mammals don't have color vision. They see the world in grayscale. And for mammals, sound and smell are much more important senses. So they don't need color. They wouldn't really trigger with them. Zebras are striped to break up their outline. A herd of them moving together, the stripes, it's hard to pick out an individual. So in that case, they're using some color, but in general, large mammals aren't colorful. If you think of colorful, I should have put a monkey slide in. There's all sorts of colorful monkeys. Think of baboons with their blue faces and red faces. But that's the primates. So, next gripe. Dinosaurs being far too big. Look at the size of that Tyrannosaurus head. As a model, an animatronic model, it's great. That's Stan Winston there. But that skull could eat him in one bite. If you go in our gallery, you get a much more reasonable sense of how big a head is. I'm longer than it. And here's another example. This is from 1953. When I was a kid, I thought this movie was great. I thought all of them were great. Now I unfortunately know better. But this is some sort of giant prehistoric reptile. Most people would call it a dinosaur, but those in the know would say, no, it's not. One of the problems is, if you tried to make it really big, look at the posture of the forelimbs. It's not erect. It's basically doing a partial push-up all the time. Here's the largest lizard we have today is the Komodo dragon. Currently, they get up to about 2.5 meters, maybe almost 100 kilos. But look at the forelimbs. Their posture is that sprawling gait. They're a bit limited in how much weight they can carry. So it's on Komodo Island. It's the top predator on the island. It doesn't have to worry about anything else. On a large continent like Australia, the largest lizard is another monitor lizard, the Parenti, up to about 2 meters. And again, I think the lizards are limited because of their posture. I'll show you shortly. It's the posture of dinosaurs that let them get big, but not ridiculously big. Again, it's not just the carnivores. We also have impossibly large herbivores from the Jurassic Park films. These stegosaurs are vastly oversized. I can easily reach to the top of the plates on the back of that thing. So this is where it can't be a Henderson talk without some math. So I'm going to show you, just try and explain why you can't scale animals up arbitrarily. There come quite literally breaking points. So also I realized at the last minute I mangled some of the spelling here. Cubic meter of water weighs up approximately 10,000 newtons. So you think 1,000 kilos of water, multiply it by the acceleration of gravity, it's about 10,000 newtons. And stress, not the psychological kind, the physical kind, is the average force acting across a surface. And if you imagine a container of water, the weight force of the water is pressing down on the bottom area of the container. So let's consider a cube of water, 1 meter on a side. It weighs 10,000 newtons. The base area is 1 square meter. So the stress is 10,000 pascals, 10,000 divided by 1. Let's double it. 2 times 2 times 2. The weight is now up to 80,000 newtons. The base area has only increased by a factor of 4, while the weight's gone up by a factor of 8. The stress is now 20,000 pascals. Let's go up one more step. 3 times 3 times 3. The weight force is now 270,000 newtons. The base area has just managed to double. The stress is now 30,000 pascals. So the message here is that the weight will always increase faster than the area needed to support it, unless you change shape. So let's look at a skeleton. Here's a human femur. The ability of bone to carry weight depends on the cross-sectional area. Bone is very strong under compression. It's much weaker under torsion and bending, as my ankle learned 9 years ago. That was Jim's reference earlier about tobogganing. Don't give in to a nagging sister. So the strength of bone depends on its composition and its microscopic structure. And that doesn't change with size. If you look at the bone and the bone cells and the detailed structure in a mouse skeleton and an elephant, they're the same. So if the skeleton doesn't change shape with the increase in size, there's going to become a point where the skeleton cannot support the body weight. You can't just take an animal and arbitrarily make it big without changing its shape. So I need to do an example. There's a really nice movie example, but unfortunately I have to go over to the dark side and look at mammals. So let's take a gorilla. Average adult male, I don't know if that's a lowland gorilla or a mountain gorilla, but anyway, it's big and strong and dangerous. It's about 1.7 meters long or tall, and that's 220 kilos. If you remember body weight, the weight of any object is proportional to the cube of its characteristic length. So here with the gorilla, we can say that 220 kilos is proportional to 1.7 meters cubed. And let's have a look at King Kong. He's more than 4 times taller than the standard gorilla, but he's got the same shape and the same proportions. So if we plug King Kong's weight into this ratio expression, how much do you think King Kong weighs? Anybody want to guess? He's going to weigh 22.9 tons. And that comes from that, if you divide 8 by 1.7, that's a little bit over 4. 4 cubed is 105 roughly. 4 something cubed is 105 times heavier. But the bad news is his skeleton's only 22 times heavier. It's too small by a factor of 5. And even if you allow a safety factor in skeletons of like 2 to 4, factor of 2 to 4, this thing still couldn't work. So I really like King Kong movies. I think the idea of Skull Island and stuff. The Peter Jackson movie, 2005, is in my top 10 favorite movies. But you have to leave your science nerd head outside when you go to watch it. So unless King Kong has a very peculiar skeleton, it could never work as a living animal. And the same applies for these things. You can't just take a Tyrannosaurus. It's already big. Come on, 12 meters. What more do you want? And make it arbitrarily bigger. It couldn't even begin to move. And the same with this sprawling thing. Ray Harryhausen did the animation on Beast from 20,000 Fathoms. The animation is great. It's a fun film. But you just don't be too overeducated when you go to watch it. Continuing my Jurassic Park slam. There's more than just the skeleton. There's other features. Animals have to lose body heat. They have to pump blood around their body. They have to circulate air in and out of their lungs. If you don't change the internal anatomy, it won't function as an animal. The same way bone strength is dependent on cross-sectional area, the force a muscle can produce is proportional to the cross-sectional area. If the heart in these things isn't increasing faster than body size, eventually there comes a point where the heart couldn't pump the blood around the body. The volume of blood that has to be pushed, the viscous drag in all the veins and arteries, the heart just couldn't do it. And the thing in the Jurassic Park movies, they have this weasel word, genetically engineered. What does that mean? It's just to try and gloss over the fact that a lot of their animals are just biologically implausible. There's the real size of a velociraptor. It's about a turkey size. I don't know why they had to exaggerate them. Anyway, I'm not making movies and making millions. One thing is, sauropod dinosaurs, it's awfully hard not to overestimate them. They are truly giant. This is Brachiosaurus. It's probably one of the ones we've got the best knowledge of. We've got 2 partial skeletons from East Africa found in just before the First World War. They really are that big. It's hard to believe they could get enough minerals to grow a skeleton and grow as super big as they do. So, Lost World movie, 1925, that's okay. Okay, next problem. Bad anatomy. Again, another movie. When I was 10 years old, I thought The Lost World, 1960, was awesome. I just loved this film. But now I'm older and overeducated, and I have problems with it. So at the top there, they've got an alligator, which is a member of a larger group known as the Crocodilomorpha, and they've stuck on horns and a sail and stuff to try and make it look prehistoric. And the bottom here, they've got a varanid lizard, member of the group Lepidosauromorpha. They've stuck a frill on it, and they've got plates on its back as well. And so you might think, yes, they're reptiles, But when you look at the relationships of these animals to other reptiles, other dinosaurs, they're not closely related to dinosaurs. Yes, they're all diapsids, so down here, the group of reptiles appear with a distinctive set of features. And a lot of these features carry on up to say that we can reunite them as a group. But the lepidosaurs and the crocodilomorphs both went on their own separate evolutionary paths, quite different from the dinosaurs. And so there's lots of features that you cannot just use lizards and crocs to be dinosaurs. I chose Triceratops over here because they stuck a frill on this lizard. And I chose Spinosaurus because it's got the sail and they glued a sail on the back of this alligator. Well, let's say a bit more about what's going on here. So I mentioned that the spines and stuff are glued on. But one of the things that really stands out is when you look at lizards and crocodiles and alligators, their posture is generally sprawled. Alligators and crocs are exceptional for brief periods. They can bring the hind limbs in. It's called the high walk. But most of the time, the forelimbs stick out to the sides. And as I mentioned earlier, bone is weak in bending. So there's all sorts of bending forces acting about the elbow and on these bones here. But in contrast, dinosaurs, the limb bones are like columns. And columns are really strong when they're loaded vertically. And so if you look at a picture of the alligator, there's two examples of why alligators are not good. They've got the sprawled limbs, comparison to the erect hind limbs of the dinosaur. And if you look at the heads, living crocodiles and alligators are all semi-aquatic. They've had to change their body shapes to live in water. Alligators and crocs tend to strike with a sideways swipe. So if your head's flat, it goes through the water better. But dinosaurs, as terrestrial predators, the skulls are narrow and tall, quite different from the alligator. So that's why I don't like seeing alligators masquerading as dinosaurs. Oops, that was quick. This is 50-second clip. So again, bland, boring dinosaurs. Check out the tail. Okay, boy, that was loud. Also, if you notice, what are those cowboys doing in the back? Absolutely nothing. They're just going around in circles. But anyway, what I wanted to draw your attention to was the cat-like tail. There's no way that could happen. I think this is another Ray Harryhausen animation. It's really well done. But again, you notice bland, boring dinosaurs. But also, that predator there, the main one is Allosaurus fragilis. And Allosaurus, along with a whole bunch of other carnivorous dinosaurs, remember, it was a group known as the Tetanura, which means locked tail. The tails are very stiff. From about here back, it's basically immobile. There's some mobility here because they need for balance and stability control. But if you go look at our Allosaurus out in the gallery, and you'll see that most of the tail is locked up. The bones are overlapping across the joints. It's very stiff. There's no way it could do that cat-like motion. And so the tail, it's thought they did need the tail. Part of it back here is anchoring muscles that pull on the leg, but it's also working as a stabilizer as well. But it certainly was not flexible like a cat's or a monkey's tail. That bugs me. Okay, walking. This is a very large alligator, I think about 5 meters long, walking across a golf course in Florida. Look at its feet. It's got big flat feet and it's walking with the heel down. The arms and legs aren't that vertical. The body is flexing from side to side and the tail is dragging. And also look at how flat that head is. That's not a theropod head. But it's mainly the posture of the limbs and the feet. And also he probably got hit by the propeller of a boat. It took a chunk out of his elbow. But it's the side-to-side movements of the body that That's very crocodilian, very lizard-like, and the tail dragging as well. That's very crocodilian and lizard. Don't use a walking alligator as a model for a dinosaur. So Jim mentioned models. Based on anatomy and footprints, we know that dinosaurs had to have walked with their limbs very erect. The bodies were very stiff. There was some movement at the base of the tail. The necks were quite flexible. So this is a model I generated years ago. I've kept the head. The head only moves a little bit to let the animal keep its vision fixed on a target. But the rest of the body has to move for balance. The red plus sign you see just in front of the hips, that's the center of mass. That has to be above the feet or above, or just ready to fall over a foot, and it has to stay between the feet. That controls the balance. And we know from trackways that theropods and other large dinosaurs, the feet were kept very close to the midline, right underneath the body for balance. If you remember from the alligator, they're out to the sides. Very different way of walking. Dinosaurs are very stiff animals. If you ever held a bird, apart from their neck, the birds are very stiff. Their legs aren't that flexible either. Just in one direction, really. So, next gripe. Too big or too hungry. We always see bland, oversized dinosaurs harassing people. And the question, here's another example. I really like Valley of Gwangi. It's a fun film. But again, it's got a large dinosaur harassing small creatures. Why would a multi-ton Tyrannosaurus or Allosaurus waste their time on something that's 75 kilos or less? It's when any animal goes to eat something, it's burning energy to get that food. If it's not going to get at least more back from the effort that's expended, it's not worth the effort. It'll die of starvation. So, time to kick Jurassic Park again. Here's Lex and Tim. Thanks to Don Christian and Tyler for body mass estimates for children. And my aquarium fish will always go for the smallest piece of, will always go for the biggest piece of food first. They're not going to waste their time on the little bits. So let's put Tyrannosaurus into perspective. Here's my Tyrannosaurus model. It's 12 meters long. I calculate it weighs just over 9 tons. There's the head. The head weighs just over 600 kilos. Let's zoom in on the head. Let's say the cranial portion is about 60%. The mandibular portion is about 40%. So that means the lower jaw has a mass of about 247 kilos. But let's wonder about the tongue. Here's some cheesy models. I needed an open mouth picture. The tongue represents about 1/3 to 1/4 the mass of the lower jaws. So they're express that in sort of a computer program expression. 0.25 or 0.33 times 247 means the tongue's going to weigh about 60 to 80 kilos. You'll remember Lex and Tim weigh about half the tongue weight. Would you go and chase something that weighs half your tongue? Large predatory dinosaurs have evolved teeth and jaws and heads and necks and the whole rest of their bodies to deal with big prey. So they wouldn't waste their time chasing tiny micro snacks. It really bugs me that they have dinosaurs chasing. It's only for drama. And so it's no biological reality at all. Okay, next problem. They're too fast. Again, here's bland, oversized, but not too oversized, Apatosaurus from the decent King Kong movie from 2005. The hideous dinosaurs from The Good Dinosaur at the bottom. But they have them running and moving their limbs in ridiculous ways. And here's my next favorite whipping boy, Jurassic Park. That's not going properly. It should be smashing through the trees. But anyway, it wouldn't happen in reality, so don't worry. Let's look at some animals today that run. We've got a living dinosaur today that runs very quickly. We call it an ostrich. And we have some mammals that evolved more recently. They can run really fast. And the first thing to notice is they've really reduced the amount of weight at the ends of their limbs. Ostriches are down to just 2 toes. Horses are down to 1 toe. And we've got a really nice fossil record for horses. You can see the evolution of the feet getting smaller and smaller and the toes getting smaller, or the side toes getting smaller and smaller down to just 1. I don't think it's anything cosmically significant, but the ostrich has 4 toes in total, and so does the horse. Anyway, so we have these two animal groups, mammal and a reptile. Birds are just glorified reptiles. They separated evolutionarily 330 million years ago in the early Carboniferous, and yet look at the hind limb of the horse and the hind limb of the ostrich. Evolutionarily, they've converged on the standard form if you want to be a fast-running animal. And these limb bone proportions, not just these, any fast-running animals you can look at. One of the things you want to notice is look how short the most proximal limb bone is, the femur, or in the case of the horse, the humerus as well. It's a very short, very strong bone. And then look at the lower limbs. The bones become very elongate, very slender. And as I've already mentioned, they've really reduced the very ends of the limbs down to just the fewest toes possible. Now let's look at the skeleton of a Tyrannosaurus. Look at that hind limb and compare it to a running ostrich. The proportions are totally different. Ostrich weighs, maybe 100 kilos, a heavy one? And the limb proportions of Tyrannosaurus are not those of a runner. And it's really heavy, like over 9 tons. And it has super big, heavy feet. It'd be really strenuous to run with big, heavy feet. There's a nice anecdote. Chris McGowan, who used to be at the ROM, he tied sandbags around his feet and practiced running and reported how hard it was. But I always thought that was amusing. So you don't even need a giant 12-meter Tyrannosaurus. Go check out an 8-meter Albertosaurus out in our Cretaceous unearthed. There's my size 10 runner. Look at the size of that foot. It needs that big foot to hold that huge body mass. I think people tend to underestimate just how heavy big animals are. Our vision system seems to be based on recognizing lengths and edges. We're very poor at perceiving that third dimension and getting a sense for the volume and the mass. And so people think that a big dinosaur could run. They're not appreciating the full weight of it. Look at today in African savanna, the lion is the biggest predator. It can manage a brief sprint and then it's done. But a cheetah, which weighs a few tens of kilos, can run and run and run. Just because you're big and muscular doesn't mean you're going to be a super good runner. I also remember seeing, have you ever watched the old Incredible Hulk movies or TV show with Lou Ferrigno? Watch him run. He's really working awfully hard to a moderate pace. He's just so bulked up. Anyway, look at the tooth-toed thing of the ostrich, a true known fast runner. Compare it to any tyrannosaur. Everything about ostriches is built for speed. There's another problem with being super big. This is a really nice paper from Farlow and Company from 15 years ago. And they highlight if the Tyrannosaurus was running as fast as Bob Barker wants it to run and it fell, it wouldn't survive the fall. The chest is going to drop about 3.5 meters, and nothing about its construction says it's built to withstand an impact force. You ought to imagine the body starts. I bet even if a Tyrannosaurus stood here and it fell forward, it's going to accelerate on its way down because of gravity, and it's going to come to a very sudden stop, and the rest of the guts in the body is going to keep coming down and pressing on the chest. It's going to collapse, and the head's got even further to fall. And they didn't just wave their arms. They used first-year physics to calculate what are the accelerations, the stopping distances, and it probably wouldn't survive. And it's not only going to be damaged going down, it's also supposedly going forward super fast. It's going to get a major road rash when it hits the ground. It's just a bad idea to have it running. And so you have to ask, why would a Tyrannosaurus need to run? It lived with large, slow, potential prey. They're as big, or maybe even bigger in the case of Edmontosaurus. The prey animals weren't running. Why would a Tyrannosaur need to run? It's just dumb. I think the reason Tyrannosaurus is so big, it needed a big, strong body to support and move that big, strong head to pull apart big, heavy carcasses. I think everything about a Tyrannosaur is dealing with large prey. And that doesn't mean it has to catch them. Even a dead body of one of these. We know Edmontosaurus lived in huge numbers. There's the Edmontosaurus bone bed just upstream from here. These animals are very abundant. And I'm perfectly happy with Tyrannosaurus being a scavenger, eating, like there's an awful lot to eat. A big Edmontosaurus weighs as much or more than a Tyrannosaurus. There's lots of meat, but what it does need is to break through a thick hide and pull apart a very large, heavy body. And those teeth and jaws connected to a big, heavy body would allow it to do that. So I just don't see why people want it to run. Again, another problem, galloping Apatosaurus. This is maybe even worse. Note the blandness. As I mentioned earlier, sauropods are big. They're ridiculously big. You have to go see the skeletons. Like our Camarasaurus is big out in the gallery, but when you go and see other ones like the Apatosaurus or the Brachiosaurus at the Humboldt Museum in Berlin, it just blows you away. But look at the skeleton of Apatosaurus. It's got the same limb and bone proportions that Tyrannosaurus does. Plus it's even heavier. It's like 17 tons. And that's not even the biggest ones. I calculate Brachiosaurus at 25 tons. There's these new ones coming out of South America, the Titanosaurs, maybe 30 to 40 tons. They're just ridiculously big. So sauropod, and also the sauropods, they've got these massive extensions sticking out of their bodies. Try and run with a 4-meter neck wobbling and a tail wobbling behind you. It's not a good idea. So, okay, I'm almost done. I saved the worst for the last. Godzilla movies. They're loads of fun to watch, but they're just ridiculous. So everything I've said so far about dinosaurs applies to Godzilla, but even more so. And here's I've got 2 extra features. This is a semi-recent, I don't know. So Mark, I saw you, it's 2014. Is there another one since? Yeah, okay. I sort of gave up watching them. They've got this thing moving super fast in the water, and it's also right at the surface. As a scuba diver, I know with all your hoses and tank and stuff, it's really hard to swim at the surface. If you have to go any distance, put your reg back in, go deep, and swim under. It's much easier. The drag forces and the loss of energy is really high at the surface. And also, the Godzilla, it's got all these plates and spines sticking out. And if you remember, the skin is really rough. None of the limbs are streamlined. And it's 108 meters long, completely unstreamlined. In contrast, look at a blue whale. It's a measly 30 meters long. But evolution, natural selection has really made this thing slip through the water as easily as possible. And also, the baleen whales, they're so big, they have to feed low down on the food web. Baleen whales have evolved to exploit krill and crustacean. But Godzilla is supposedly some arch predator, supposedly eating big things. It wouldn't work that way either. So hydrodynamically, it's terrible, and ecologically, it's terrible. No wonder it went extinct. But anyway, one more, Another problem, maybe not so obvious, is that large animals are at risk of overheating. You always wrap up babies because they've got such a high surface area, because they lose heat much faster than an adult. But once you get really big, losing heat becomes a problem. Come back to good old Tyrannosaurus, 12 meters long, just over 9 tons. From my model, I calculate it's got a surface area of about 52, 53 square meters. And whenever you move or walk or do anything, you're generating heat. Doesn't matter if you're an ectotherm or an endotherm. So we're endotherms, we have our constant body heat, but even large animals will, cold-blooded things will produce heat from movement. So when you divide the surface area by the body mass for Tyrannosaurus, it's got about 5-6 square meters per ton of flesh to help it lose heat. Godzilla, 108 meters long. What would happen to the ratio for Tyrannosaurus if we made it 108 meters? It's now down to just over 1/4 of a square meter per ton. It would probably die of heat. Tyrannosaurus would certainly die of heat stroke. And if you look at Godzilla, it hasn't got the nice slender legs or tail that the Tyrannosaur has. There's a lot more mass packed inside Godzilla than there is in a Tyrannosaur. So the super chunky Godzilla would probably expire from heat stroke before it even got to 108. So there's all sorts of things about body size that limit what animals can do or how big you can make them. So No. And I'm done. Okay.